In the previous video, we studied that when we have 2-point charges Q1 and Q2, they exert electrostatic forces on each other, and the value of this electrostatic force is given by Coulomb's law. Now, as scientists studied further, they noticed that if I have a moving magnet, so this is my magnet moving with a velocity v near a charge, this moving magnet also exerts an electrostatic force on this charge. So we have electrostatic forces in both the cases, and for all purposes the nature of these forces is exactly the same. And so when scientists wanted to just focus on studying the electrostatic forces, because of the different laws that governed their behavior in different cases, they could not form a uniform theory. And so they wanted to get an abstraction which would help them to focus on the electrostatic forces and not worry about the cause always. And so there was a great scientist called Michael Faraday. He noted some very interesting phenomena, and what he noted was, let's say I have a charge Q, and at a distance r from Q I place a charge Q1. Then the force exerted by Q1, let me call it F1, is given by Q1 over r square. We know this from Coulomb's law, right? Now say I get rid of Q1 and I place Q2 in its place. I remove Q1, place Q2 here. Then the force exerted by Q on Q2, let me call it F2, is given by Q2 over r square. Now if you notice these two equations, what you see is that this part KQ over r square is common to both the equations, and only the effect, the Q1 and Q2 change depend on what charges are experienced the force. So Michael Faraday said that instead of thinking of electrostatic force as interaction between two charges or interaction between magnet and a charge or something else, you can think of electrostatic force as if it is made of two parts. One part is causing the force and the other part is experiencing the effect of the force. So in our example, when Q is exerting a force on Q1, Q is the cause of the force and Q1 feels the effect of the force. And he said that if you want to just study the effect of electrostatic forces, if you just wanted to study how electrostatic forces act on different charges and what they cause in them, then you can separate them, and to do that he introduced an abstraction that he called as electric field. An electric field is defined as the force experienced per unit positive charge at a point. So it is the force per unit positive charge. By unit positive charge we mean a charge of +1 coulomb. And so what this does is an electric field defines the effect of the electric force for one charge, and that is defined as E is equal to F over Q, and obviously its units are Newton per coulomb. Now you must remember that electric field is just a concept. It is not a new physical phenomena. It is a force per 1 coulomb of charge at a given point, and so electric field is just an electrostatic force, and it is a vector in the direction of the force. So let us see how this helps. Say I have a point A, and I have found out that if I place a charge of 1 coulomb at point A, the electric field is the force it experiences, which is the electric field, is, let me call it 2 into 10 raised to minus 3 Newton per coulomb. Now if I want to find out what will be the force experienced by a charge of 2 millicoulomb placed at this point, then all I have to do is 2 into 10 raised to minus 3, that is 2 millicoulomb, 2 into 10 raised to minus 3, that is the electric field, and that I get as 4 into 10 raised to minus 6 Newton. And so without knowing the cause of this electric field, I have no idea what is causing this electric field. It could be a point charge, it could be a moving magnet, it could be a very complex distribution of charge. I do not care. Once I have experimentally or theoretically established the electric field at a point, I can just study the effect of that electric field, the force it will exert on different charges at point A, and I know how that will behave. Now say if I have Q is equal to minus 2 millicoulomb, what happens? if I have minus 2 millicoulombs, I get 2 into 10 raised to minus 3, that is 2 millicoulomb. 2 into 10 raised to minus 3, that is my electric field, and that is minus 4 into 10 raised to minus 6 Newton. So what this tells me is that the force is of the same magnitude, but it acts in the opposite direction when the charge is negative. And that should not be a surprise because it comes from the definition of electric field as the force per unit positive charge. And so the force on a negative charge will be in opposite direction. Now let us see how we can theoretically establish the electric field. So how to establish an electric field? Let me consider a point charge. Say I have a point charge Q and I want to know what is the electric field at a distance r from Q. So one way to establish it is experimentally. To do that, I place a charge of 1 coulomb here, measure the magnitude and direction of force that this charge experiences, and that is my experimentally measured electric field. Another way is to find it theoretically, and to do that, I know that by Coulomb's law, the force experienced by 1 coulomb charge can be given as kq into 1 over r squared, and hence I can write my electric field at this point is kq over r squared. Now this is just a magnitude, and since electric field is a vector, I need to know what the direction is, and the direction is given by the unit vector r cap, which is defined as the vector acting from Q towards my point of interest. And so here this is my r cap, and this gives us the electric field of a point charge. Now one thing to notice here is that the electric field depends only on the charge that is causing the force, and so even if there is no charge at this point to experience the effect of that force, the electric field always exists at that point. That is analogous to gravitational field, as in the gravitational field, say, of Jupiter exists as long as Jupiter exists, even though there is no object, say even though there is no person around to feel the effect of that gravitational field. And so we can say that electric field is the property of source charge only. One more thing to notice here is the direction of electric field. So if I am talking about electric field due to a positive charge, say at a point at a distance r, then since the force it exerts on a unit positive charge will be repelling, electric field acts away from the positive charge. So electric field acts away from positive charge. On the other hand, if I had a negative charge, then the force it will exert on a unit positive charge will be attracting, and so my electric field will act towards a negative charge. And one final thing to notice is that if I have a point and I have two fields acting at that point, say at some point there is a field E1 due to some source and there is a field E2 due to some other source, then you should always remember that electric field is just the electrostatic force per unit positive charge, and hence this is two forces acting at a point, and the resultant force is the vector sum of these two sources. So I can write ER as the vector sum of E1 and E2. And so that's it.